Okay. Yeah, so hello, everybody. Welcome to week 4, the final week of AI summer. And this week, we're going to focus a little bit more on the ways that you could take models and maybe adapt them even more specifically to your needs. So last week, we had really great sessions about LangChain, where we learned a lot about, helping to use these models even better to your specific needs. But there is this other step that you can take to suit models to your needs, which involves specifically fine-tuning a model to your exact data, or taking a particular model that maybe wasn't trained to do a task that you want and using it to train the task that you want. And that is going to be our focus for this week. So today I'm going to be basically taking you through how we can take models off Hugging Face, talking a bit more about Hugging Face, which is the amazing platform that hosts all sorts of models and data sets for doing this type of work. And then we're going to talk about how to run inferencing on our models, start to think about fine-tuning our models for our specific use cases, and all of that really good stuff. So in the chat, I've posted a link to the GitHub, but also to the specific first notebook that we're going to be working off of, if you want to go ahead and open that. Although before we get started on this notebook, I want to just talk about the Hugging Face website in a little bit more detail. So let me go ahead and share my screen. Okay, and can everybody see the screen? So where is the notebook? So this is the first notebook that we're going to be working off of. There should be this open and collab button that everybody can use to open it, and then you'll get your own version and can be running everything on your own. But the first thing that we are going to talk about today is inferencing models with Hugging Face. But like I said, before all that, I want to just kind of talk about Hugging Face in general as a platform that hosts all sorts of models and data sets and is just a really great tool to use because of that. So you have probably, Hugging Face. No, I don't want Flash models. You've probably been to the Hugging Face website, of course, because you have a Hugging Face token. But there's a lot going on this website that sort of can help with kind of all steps of model development. So the first thing that I want to talk about is this models tab. So Hugging Face already has on it, a bunch of people have uploaded models, and sometimes the original version of models people have uploaded, sometimes people have fine-tuned a model for a specific use case. But as you can see, there is this ginormous number of models on this website, all of which are these incredibly powerful transformer models, which are designed to do these tasks super well. And on the left here, Hugging Face has this really great way of interacting with this page, because 214,000 models is obviously a lot. And also model names are oftentimes very much not descriptive. So if you're looking for a particular model, that's great. You can come up here and just filter by name and start to type like BERT, because I know that that's the model that I want. But a lot of times you maybe don't know exactly what model you're looking for. You're not looking for a specific one. And sometimes this name is not particularly helpful, and maybe you won't know to search for that. So Hugging Face also has this great thing where they put all these different tasks on the left here, and you can search for a model by selecting a task. So you can say, I'm doing natural language processing. I want a model that will do question answering. So I want to be able to ask it questions and have it respond, versus something like text classification would be, I give it a piece of text and it tells me something about that text, like, oh, that has a positive connotation or a negative connotation. And just by clicking on that, I get a list of models that are specifically trained where that is the target task. And a lot of models on Hugging Face, a lot don't, but many models on Hugging Face have this great thing called a model card, where there's a brief description about the model. A lot of times it covers ways that it was trained. A lot of times there's a small note about how to use it, which we will talk about how to use it because it's very easy to use Hugging Face models. But a lot of times they put that code right in there for you. And then there's also this cool thing called the Hosted Inference API, where Hugging Face hosts for you a little way to interact with the model. So because this is a question answering model, you can just type right in here directly onto the website, some sort of question and context, and then it will, from the context, answer the question. And that's specific to question answering, but if we went back and we chose instead text classification, I can choose a different model. And if it has the hosted inferencing, that will instead be targeted towards that task. My internet is being a tiny bit slow, so this page does not want to load, but that's okay. So in general, this is an amazing way to filter through models. If you want to, you have a particular task that you want to do, maybe you want to look through what models already exist for it. You can read the model cards and see how people have sort of dealt with that exact problem. So this is finally the sentiment analysis. The text classification is loading, so we can type a bit of text and hit compute, and it tells us labels for this bit of text. Okay, so that in general is models on Hugging Face. So there's tons of options there. And again, we'll be picking a specific one of these and inferencing on it and then fine tuning on it in a little bit. But there's obviously, like I said, tons and tons and tons of options for models, which is very cool. The other thing that we have here that I'm going to talk about right now is data sets. And data sets are also designed with tasks in mind. And these, again, are sometimes collected by the groups who train the models, and they make this data available and the full data set that they trained a model on. Sometimes these are just collected by people. They find a data that's really interesting. So you could upload a data set to Hugging Face where you have structured it by having examples and labels or whatever. And sometimes there's a few that I think are like Hugging Face example data sets. But again, there's this gigantic number here of just tons and tons and tons of data sets. And like with the models, you can filter the data sets by the task that you want. So again, we can go to text classification, and then something called Amazon reviews is likely a data set of Amazon reviews. So the text of the review and the reviewer ID and the number of stars that it gave, and then a product category. So you could use this to, for instance, train, given the text of the review, how many stars did the reviewer give? And that would be a text classification, or given the text of the review, what was the category of the product that they are talking about? And so this is a data set that is good for text classification. Again, there's a data set card, like there is a model card often, sometimes not. And a lot of times there is this data set preview that allows you to actually look at the data. So this one is maybe means multi-language. A lot of these are in a language that I personally don't know, so I would pick a different data set if I were training a model. But if you wanted a multi-language data set. And I think that, again, the data set cards are like the model cards, where it's a lot of times up to the people to create this data set card in order to explain to you what the data set is. So for here, we could, read, yes, that the data set does contain all sorts of languages. And, this little tidbit is going to tell us all about the data set and help us better understand if it suits our needs. So that is kind of what I'll talk about in terms of Hugging Face and interacting with the website right now. And let's talk now, go to over to the notebook and talk a little bit about how we would actually use one of these models. So Hugging Face has all of these models. Let's say I, look at GPT-2 and I'm like, wow, this looks amazing. This is like the task that I want to do, and this output looks great. And so I want to like start actually interacting with this model better. Then maybe the first step that we would do is just basic model inferencing, which is the first thing that we're going to talk about, is inferencing with our models through code, and grabbing those models off Hugging Face. So I will one final time post this in the chat just in case anyone came in late and did not get it. So we're talking about inferencing only on Hugging Face models, and we'll talk about fine-tuning Hugging Face models in a second. So we can go ahead and run these cells. This one is the classic, we have to install a bunch of stuff, and that will take a minute. And then we also need to import those things after we install them. And I have a cell here that just makes things print prettier. Honestly, I copied this from someone on Stack Overflow, but it formats things. Google Colab does not like to have your text strings not wrapped, and it's very annoying. So that's just going to do that for us. And then, of course, we have our Hugging Face token. When we're interacting with Hugging Face, it's always just easier to be logged into Hugging Face. Remember that after you run this cell, you can follow, it'll pop up with this little window, and you can follow this link, which will take you just directly to your tokens page. I have 3 tokens. I don't know why. I always use the right one. I should delete the others. And you can just copy your token using that little copy button and go right back in here and stick it in whenever we finally get to this point, because we are still installing and importing lots of stuff. While I am waiting for these few cells to run, are there any questions that anyone has so far about just like Hugging Face as a website type of stuff you can do with it? Awesome. Okay, so I'm going to stick in my token, and we are going to finish logging in. Okay, so the first way that we are going to do inferencing with Hugging Face is using these built-in classes that Hugging Face has for particular models. So I pulled out GPT-2 when we were on the website. I said, I think this looks like the model that I would want to use. And so now I want to actually get to using that model in code. And it turns out that for certain models, particularly kind of popular architectures, models that people will tend to kind of fine tune, but that have the same base architecture, Hugging Face already has these built-in classes. So they have this built-in GPT-2, base model, and the GPT-2 tokenizer. Those already exist as classes of a model inside of the Hugging Face transformers library. And that makes it really easy to load in a model, because this single line of code here, where we set model equals the model class that we want dot from pre-trained, and then we input the name, that is all that it takes to just load this model off of Hugging Face. And Hugging Face will go find where that model exists on Hugging Face, grab it. Really what it's kind of doing also is looking in this config.json file to figure out the configuration specifically of the model. And then it's going to download everything that it needs, and we'll have our model loaded that way. And we can do the same thing for the tokenizer here. So when we have text inputs, we need to do a particular tokenization so that the model is able to look at them. We have to turn them into numbers because that's what models understand. But similarly to just loading the model from pre-trained, we can also just load the tokenizer just as easily. So we stick in the target model name and we have loaded the tokenizer. So we are going to, for our inferencing, oh yeah, we had a question.
Yeah, like if you go up a little bit,
yeah,
in just the previous section, it says we are using GPT-2, not GPT-2 medium, large, or Excel.
Yes.
I thought GPT-2 was like one model trained on, like a black box trained on one set of data. So what does it mean for us to have different GPT-2 models?
So a lot of times with these large models, they release different versions of the model, which really is just a different number of total parameters in the model. And the larger the model, the more parameters tends to be kind of the better at generalizing and the better performance. So with GPT-2, they released these different versions of the model, which all kind of have the same base architecture and data that they're trained with, but there's a different total number of parameters in the model. So GPT-2 is the smallest version, but GPT-2 medium, large, and extra large are all additional versions of GPT-2 that get increasingly bigger. And so we're running on Google Colab, but if you had some sort of like beefy GPU, you could try to grab one of the larger versions of this and see if you could run that.
Got it. And so the medium, large Excel is all from OpenAI. It's not like a Hugging Face thing that they've created for GPT-2.
Yes, I believe that OpenAI releases them.
And this predates, right? So this is the original tech. GPT-2 was where OpenAI came from, really. So this is the early stuff.
Got it. Thank you.
Okay. Yes, so GPT-2, as we saw, is a text completion model or text generation, but you give it, a starting sentence and it will finish that sentence for you. So we want to define some sort of input text, which is, a little taste of something, and then let GPT-2 finish it for us. So this is going to be the input text, once upon a time in a land far away, a very classic beginning to a story. And that is what we're going to see, what GPT-2 fills in the rest of this for us. So once we take our input text, we need to run it through our tokenizer just to get what we're actually going to put into the model. And so that is this object input IDs. And if I print out input IDs, you can see that this is now a set of numbers, not a set of words, because models need numbers. And in here, you can see that we have 9 words and 2 punctuations, which is a total of 11 tokens. And if we count here, we do get a total of 11 tokens. And you can see that this 11 must be the token that corresponds to a comma, because we have once upon a time, comma, in a land far away, comma. You could see that repeated word A must be token number 257, because once upon a time, comma, in a land far away, we have the repeated number. So we can see that the tokenization makes a lot of sense, in that we expect our tokenizer to work like a dictionary, where for each word we have a lookup number that corresponds. And that is how we are turning our words into numbers, roughly 1-to-1. Although I do make this note in the notebook, though, to remember that tokens aren't always 1 word to 1 token mapped. So a lot of times when you hear that a model has, like 4,000 context length, and that means it can accept 4,000 tokens, 4,000 tokens does not equal 4,000 words, because the way that words are tokenized is to be a little bit scrappy about the way that you break down words. And so here I have a couple of examples of, in particular, maybe like this second line. If we were to tokenize this line of text, firmly, firm, enjoyment, enjoy, you can see that this is firmly, and then a period, and then firm is the same root word, but you can see that that ly is an extra token. So firmly doesn't get its own token. Instead, we take this ly token and we stick it onto firm. So kind of, I don't know if you would call that a compound word. I guess that's not technically a compound word. But whatever the word is for words where you stick on that little end to a word, those have kind of separate tokens for that little extra appendage. And so in these cases, these two sentences is not as many words, but it does result in additional tokens because this will get tokenized as 2 words. And so will this, for instance. And then also punctuation, of course, does count as a token.
Okay. So it's interesting that enjoyment and enjoy have the same token.
Yeah, so that is, so enjoy and mint, and then this is the period token. And then
sorry, I
again.
forgot that 434. Okay, got it. I thought it was. There you go. That makes sense.
Yeah, and then up in this top one, you can see that the apostrophe S is its own token. So it apostrophe S, the it gets repeated, and the apostrophe S shows up again here, and that's so.
I guess this is just the OpenAI, their tokenizer doing this way. I guess if you choose a different tokenizer, they probably would do these things a little bit differently, correct?
Yes, I think so different tokenizers do have their own subtleties. I do think that this is a fairly common way to tokenize text, though. Somebody else can chime in, but I do think for the most part, all tokenizers do this sort of thing, but maybe some particular words I think are harder to do it with. Enjoyment, you just stick like, but shape versus shaping, now that root isn't exactly the same thing.
It's really a brute force and statistical method, right? And so this is very different from like stemming that you might be familiar with from older styles of NLP. Holly was just asking about special tokens for compounds and how do you handle polysemy, but the answer is no. You're right to all of it, because it's really just like a brute force question where you try to optimize and to have the lowest number of tokens per word, because you don't want to do it at the letter level because that's way too many tokens for each one. And you don't want to have like every word have their own token, because then they don't seem to be related and it's harder to learn any of many of them. So really, I mean, there's not a whole lot. As a matter of fact, if you try to design tokenization to do better, you usually do worse than the pure statistical. So it's, the answer was to do it in as dumb a way as possible, and then all the polysemy and all of the richer meaning happens later from is learned during the training from the transformers later on. So all that other goodness you get from the transformers, it just needs to have the first. All it needs is that first pass, into numerical tokenization. That's all that the transformers needs, and then it takes and runs by itself. You can have other bad downstream effects, like if you don't take into account other languages, like GPT-2 didn't do a great job of taking into account all the different languages that it could be trained on. So that means it's better on English than most other languages, because it takes too many tokens to represent the other languages.
We have another question.
Hi. Yes, does that imply then that the tokenization that occurs will be dependent on the data set as it's introduced? So if you have one document, then your tokenization output may be different than if you have that one document as a series of, let's say, 3, 4, 10, 100?
Do you want me to answer that one, Abby?
Yes.
Okay. Yeah. So really, often what happens with tokenization is you take a sample of the data set that you're going to be training on. And remember, you only get to do it once, right? The minute that you begin training, you're locked in. So that's the tokenization you're going to be stuck with. It usually, I mean, studies have shown that doing a good sampling is really has no, there's no benefit to trying to do it on an entire training data set. Doesn't seem to help. You have a good sampling, and then you optimize, number of tokens, minimize number of tokens per word, then it does a pretty good job. Smart approaches also do that on the various languages that you know you're going to be training on. So you don't just do minimization of tokens per words. You might take a look at that across all the different languages that you're going to be using. So you specifically sample in a way that it faithfully represents the mix of languages that you're going to be using. And then there are lots of other approaches as well. But the fact is, once you do your tokenization scheme, it is married to the model. And that's why it's really important that you get the right tokenization scheme to go with the model. Abby, I think you had another question.
Yeah, certainly.
So I guess
And
I
Holly,
thought I
you
understood that. Sorry.
Oh, Michael, Holly was asking, but she is muted.
Okay.
No, I'm not. I keep focusing on the hand thing and I forget to unmute. So I keep reading about AI training sweatshops where humans are deeply engaged in this, and so the sort of the socioeconomic capitalist collateral damage, right, of AI. When is that happening? Is that happening at the very beginning with assigning tokens, or where, or is all this initial tokenization happening pretty much automatically?
You want to take that one, Abby?
Yeah, okay, so Jesse maybe can take over because I don't know too much about this concept of AI sweatshops, but I don't believe at the tokenization step it would happen. I think a lot of times you just build this dictionary of how a word maps to a number, and then you can just run it on all of the text that you would have. So that step is usually not the particularly kind of complicated or intensive part of this.
Yeah.
But then
You're exactly right. It's a purely statistical technique, and you don't need to have people doing it. Where you do run into this, and you have it a lot more with prior iterations of AI, because prior iterations of AI did not use self-supervised learning, right? And so if you want to train, if you needed to train a convolutional neural net and so it could do images, you needed over 1 million labeled images, millions of labeled images. So that means a human looking at that saying cat, plane, dog. And that's where you have the, oh, and by the way, you're going to make 0.01 cents per image that you do. So you might want to, really buckle down, because you're going to be doing several thousand of these so you can have lunch. That's where that really came in. Self-supervised learning, you still have it, but far, far less, because if you think about it, all you're doing is you're removing a word and then having it guess what the missing word was. That's not a human. So where you do find it again is human feedback. So reinforcement learning from human feedback and anything where it requires labels. You're beginning to see less of that, because what you're finding is that larger models work really well for creating new training examples from fewer human created ones. So you can create lots of new ones with a more advanced model. That's what Stanford did with Alpaca. They did their instruction fine tuning by using much larger models to say, here's several thousand examples, create new examples for me. So it's happening less and less.
we have other questions, Michael?
Yeah, I guess I thought I understood the tokenizer, but then after a little bit more, then I get confused again. So I guess a couple of assumptions, right? I thought I read, with the ChatGPT 3 or 4, they have a vocabulary is about 50,000, around that, right? I guess that's where the tokenize actually happened. So then, well, the tokenizer is according to the vocabulary, right? The lookup, almost like. But then you also talk about that, every time when you do the tokenizer, you actually also do the sampling as well. I guess how these two married together.
Wait, sorry, can you repeat that last part?
Well, what I thought, if I'm going to do the tokenizer, is just, let's just say I have a 50,000 vocab, right? I associate with each word with a number. Then my tokenizer is just do a static lookup, right? But then you talk about this, the sampling and so on and so forth, almost like, you're doing that dynamically.
You do that first, right? So first you have to figure out what numbers are going to represent what words or parts of words. So you only have to do that once. That's a statistical question of just that one time. What is your, that's how you build your lookup dictionaries for tokenization. So first you have to build your dictionary, and you're going to decide that like enjoy might be one, that might be one token. Another tokenization scheme, because you had other training data, might find that actually it works better to tokenize in and joy separately. And that's what I mean by purely statistical question. Once you define that, in is 43, joy is 932, you're done. Then it's always a lookup table from that point forward.
Well, but the thing is, you know, for example, right now, you only have the second input, you only have forward. Or if you want to tokenize, you probably have like about 7 or 6 or 8, right?
Well, but
how you translate to that 50,000 vocab?
Well, that first, so the very first thing that you do is you decide how large your dictionary is going to be. So they decided here that it's, then this one, I don't remember how big this one is for GPT-2, but they said, okay, I'm going to shoot for about 50,000 tokens. I'm going to give myself a budget of 50,000 tokens. Now here's a sample of, you know, all the text that I think I'm going to be training on, but I'm just going to sample from it. Come up with a numbering scheme for me that will minimize the number of tokens per word, and then it's set. At that point forward, once you define that dictionary, you don't do any more sampling. You don't do anything more like that.
Ah, so the 50,000 or whatever that is just their upper limit. It's not always use that 50,000.
No, you can have much smaller. You can have much larger as well.
Well,
so, and that's dependent on the architecture that you choose, right? The attention scheme you might have. Some schemes like Perceiver IO have like huge amounts of dictionary space. And think about multimodal models. Multimodal models, you're not only breaking up words, you're also breaking up images or sounds, right? And in that case, you have a token for, you know, for this pixel space right here. That's a token, you know, ENG is a token, you know, bleu is a token, right? Multimodal.
I see. Got it now. So in other words, that 50,000 is really not a limit. There's no such thing called limit. Okay.
Yeah. But once you decide, then it's fixed, right? You decide as you're planning all this out, then that is going to be your capital L. That's going to be the size of your token dictionary.
Got it. Thank you. No.
Okay, Joshua.
Yeah, thanks. One more question on tokenization. If you're using ChatGPT for something like languages, so you're stuffing in a chunk of Python code, for instance, are you penalized for, in terms of it counting for more tokens, for kind of the idiosyncrasies of Python's syntax, like every punctuation, every open bracket is its own token, and even more so, like if you name your variables _1, you know, semi-gibberish, you've now got to like token semi-character by character. Like, is that true? And is there, like, do you need to do some pre-processing if you want to minimize your token?
So I don't know if Jesse will know better. I do believe, though, that yes, for generating code, like every bracket is just the bracket token in the dictionary, and it understands as it constructs code, you know, that how to write code because it needs brackets in certain places and underscores in certain places. But I think that you do, yeah, at the token level, still have to just stick in all of those punctuation that you expect in code and all of that just as tokens into the model. As for if there's anything you can do to reduce that load, because there's obviously a lot of punctuation, I don't really know. Do you mean in terms of like, if you know, your model can only like output 1,000 tokens and now you're worried that like half of them are wasted to like a single parenthesis,
yeah,
type of thing?
Well, that, and also for variable names. I mean, should we go back to naming things X because it's one token instead of, you know, instead of naming it something more complicated and descriptive?
Yeah, I don't know. It is a good question. I think that maybe a reason people aren't too concerned about it right now is I think the models that are particularly good at writing code right now are these very, very large models that already have, a context length of like 8,000 or something. So they're probably able to write, several lines of code without that really being an issue because the context length is long enough. But yeah, maybe that is something that you would consider if you had a model that, was able to write you really good code, but had a super small context length, that maybe you would ask it to shorten all the variable names as much as possible or something in order to better accommodate that. Or I don't know, ask it to do like list comprehensions instead of for loops when you could, because that tends to be shorter or something to that effect.
Got it. Okay, great. Thank you.
And I'll mention one other thing, which is interesting, is that GPT-2 did not encode or do not encode. This is true. I think this is true. I don't remember now. I think it was GPT-2, might have been another one, did not encode spaces well. And so it had real problem with generating Python code because it didn't, you know how important tabs and spaces are, to get it right, the embedding right, the indenting right and so it was a real problem. GPT-3, of course, not a problem. GPT-4. One other thing to keep in mind, and there are a couple of other comments that are coming along the side, is that almost in a good tokenization scheme, you almost always can get all the way, you can tokenize and get all the way back to the original text with few changes, right? So it can be a two-way street, which is not the case with the old style lemmatization and stemming. Once you stemmed, you lost a whole bunch of information. This is, you're not losing the information. And Holly, you'd asked again about polysemy and about, sort of capturing the multiple meanings. At tokenization, you got none of that, right? Yes, the encoding exactly the same, because what's not happening yet at that point is the context. It's not going to take into account the context. That happens later in the encoding or the decoding stage, depending which model you're talking about. GPT-3, for example, is a decoder-only model, and so during those those transformer stacks, that's where you literally re-represent the words. The tokenization really is just like a number. It's like a lookup. And the first thing that happens early on, once you get 43, right? 43 is your tokenization. The very first thing that's going to happen is that it's going to do its initial embedding, which is it's going to do a lookup. Okay, what is my 43rd embedding? Oh, here's my embedding 43. Okay, then I'm going to do my first transformer stack, and now that's going to subtly shift that embedding to something else depending on all the words that were around it. Remember, attention does the blending of those embeddings. So if you do that, and if you try to get that same word back, it's probably going to change. So you might say the exam was hard, and you do all the encodings, and when you get to the end of the transformer, if you try to get it back, it would mean something closer to difficult. But if you said the road was hard, oh no, that could be metaphorical. So it could be the asphalt was hard, right? Then you're going to get something which is going to be more like did not give, was not forgiving, right? So that type of informing from the context happens just later. It does not happen. Tokenization is just dumb. It's just like you're coming up with a single lookup for it. Is really what's the only purpose that it's solving.
Okay. I will continue on through the notebook then, but yeah, feel free to ask any more questions about tokenization as they come up or in office hours, because I know that it's a it's a huge part of training models and it's a lot to think about. Okay, so now we have our tokenized input, so we can now give our tokenized input into a model because now it's in a format that a model understands. And giving a input to a model, so remember we very simply were able to just define the model here, call what type of model it is and say from pre-chained and give it the model, which exists right here on Hugging Face. And now we have the model, and all that we have to do is do a model.generate, so a very simple line of code in order to now create an output from that model. And so this input IDs is that tokenized input. not this one, because this is the one we were messing around with, but this one, which is Once Upon a Time in a Land Far Away. This maximum length is just the maximum length of what it is going to generate for us. So you can just, I've set that to 100 so it doesn't write too much. And, oh, sorry, I cannot see the, and I actually do not, I think do sample is how much kind of creativity to give the model. So you're able to set this do sample parameter to false. And I think that that will give you a more like deterministic output. But if you do sample equals true, then if you run this line of this cell of the code very often, you will get kind of a nice diverse set of outputs. You'll get some creativity out of the model. This pad token ID is just, we have to set that so that we don't get a warning, because warnings are ugly and we don't like them. Okay, but we get the output from the model through a simple line of code. And then again, we were just talking about this, that we use the tokenizer now to re-decode our output into something that we can read. So our output, and I've printed it down here, actually, what the output is going to give us from up here. This output is just a bunch of numbers again, because the output from a model, of course, has to be numbers. So the tokenizer also has a built-in decode option, which is just going to turn whatever the model generated back into a sentence for us. And here we can rerun this actually, because it's, oh no, I never ran this line. We can rerun this because inferencing a model is a very quick thing to do. And it should tell us, we'll print out this generated text. So it finishes this for us, Once Upon a Time in a Land Far Away. That is what we gave it. But now it is going to say, the Lord said, I will destroy my enemies when people have been put to death. And it's, you know, filling in the rest of this story for us. And you can, like I said, we can rerun this section, and we get now a different story. So once upon a time in a land far away, a man's words will be heard by 3 or 4 millions of the men in the colonies. I think if you run a lot of these, you'll come to see that, you know, GPT-2 is not like a particularly great model. It doesn't give you like super interesting stories, particularly this smaller GPT-2. But the sentences are always very, you know, coherent. It makes sense. The English language is being followed appropriately. So it's still, you know, incredible that it, from this little beginning, will kind of make up all of this stuff that is coherent and makes sense. Okay. Oh, do we have a question, Chris?
Yeah, I think you mentioned that I guess we're focusing on inferencing today. By that, do you mean like that we're focusing on next word or next sentence prediction? Or does inferencing here mean something else?
So yeah, inferencing here means taking a model as is and just getting outputs from the model. So right now we're talking about inferencing. Actually, in a bit later today, we'll talk about fine tuning. So I'm making this distinction between inferencing and fine tuning, because in inferencing, we're just grabbing a model and we're running that model on some set of data. So it's like just a forward pass of the model. But in a minute, or in a few minutes, we'll talk about fine tuning, which would be taking a model and having a data set and saying, now I want to use this model, but I'm going to train it a little bit extra on a particular data set to do some other task for me. And so if you have a model that you just want to work with right out of the box and that model already works great for you, then you would just do inferencing and you don't have to worry about sort of that fine tuning step. But sometimes when we go through this inferencing step, we find that the model doesn't work as well as we want, and we might want to perform some additional fine tuning on either extra data or on a different task or something like that. And so that's kind of the distinction there.
Thank you.
Okay. So the other kind of way of interacting with these models which is really cool, is through Hugging Face's pipeline functionality. So up here, we talked about kind of, I want to run GPT-2, so let me grab, from transformers, they have this particular GPT-2 class and this GPT-2 tokenizer class. But I also mentioned that these models come with, sorry, I lost my place. These models come with this config file, which tells Hugging Face about the model. And we can actually see this file if we go into GPT-2. We've been talking about the model card, but there is this little files and versions tab. And in here, there's typically a config.json file. And you could just open this up and look at it. And it basically has everything that Hugging Face needs to know about a model to set it up. So actually, even here, we see this was the vocab size for GPT-2. So it had a vocabulary of around 50,000 words. But we can also see, like the activation function, that's, some info, the model type, but we can see that inside the config.json, actually, the architecture is already specified. So Hugging Face shouldn't need us to do this digging, right? If it can see the config.json, it should already know that this is the type of model that it is. And it turns out that Hugging Face has done that for us. So they have this high level pipeline functionality where actually they say, okay, you don't even have to tell me what type of model it is. You just create pipeline on task you want, or down here, you can do pipeline on model you want. And I'll set up everything for you because I'm going to look through that config.json. I know the models that I have on Hugging Face, and I'll figure out how we have to set that model up. So here is a different way of interacting with the model through that pipeline. Pipeline is just something that you import from transformers. And I think that we did that up at the top, from transformers import pipeline. So it's just this already kind of existing functionality inside of the transformers package. And the cool thing here, so this second example is kind of more similar to what we just did above. So we set, text generator equals pipeline, and we've specified the exact model that we want. In this case, GPT-2 medium, or this would work with GPT-2, which is what we did exactly above. Give the same input text. And now we actually don't even have to define the tokenizer, because again, it knows what tokenizer it needs to grab, and it's going to do that for us. But the other cool thing with pipeline is that, let's say I know I want to do text generation and I don't know that I want GPT-2. Like I'm like, oh, I don't know. I just know I want to do text generation. You can not even specify a model, but just specify a task and say, I want to do text generation. And Hugging Face will say, okay, you didn't give me a model. I'm going to pick one for you. And so in this case, it ends up defaulting to GPT-2. So we're going to get GPT-2 anyway. But you don't even have to, you can just tell it, I want to do text generation, and it will handle everything else for you. Michael, did you have another question?
Yeah, I guess that's, you sort of explained it, but I would assume that there are multiple models that can does the text generation. I'm wondering
Yes.
how Hugging Face decided to choose GPT-2.
I don't know exactly how it chooses. I think that they just have set somewhere like what they're going to pick as the current default for each of these, which I think is maybe at the crux of like performant and small enough that, like you don't have to be on some super incredible computer in order to run it, because most people interacting with the pipeline won't necessarily have an incredible computer. So I think that what this default is going to be is just Hugging Face has set it and has picked for each of these tasks a model that they think, performs well, but is also able to run fairly quickly. But you can go into text generate, like, here on the Hugging Face website, you can go into this text generation section and, choose this model instead, and give that in this line, and it will, again, do all the setup for you seamlessly.
And also where I can look up all the can you scroll up a little bit, like, for example, task, because you can pass the task argument, right? What all, is that a free text, or you actually have to choose from an enum thing?
There is a set number of things you can give to that task, which I thought I linked the documentation to pipeline, but I maybe didn't. But I believe in the pipeline documentation, they do just list like what can be fed into here. And it is most of the, I don't know if this is the right page. Oh, it's maybe over on the right here. These are the supported tasks. So these are like the supported natural language processing tasks. We'll talk about in a second. It actually also supports, computer vision and audio, of course. But I think that these are the tasks that are kind of, you can call by name. But where there's a list of names, I think I've seen before, but it might be like somewhere you have to dig through the source code or something, which is frustrating. Oh, so here it says, yeah, that this one can be loaded using a task identifier. I don't know if they have a list of all the task identifiers somewhere, if you just have to dig through this, or I don't know if someone else knows who has used this. Yeah, and then I think I was going to say that it is an annoying thing though, because I think that all of these tasks are supported. So like, table question answering, I think is supported, but I think it's not always obvious like how to call it. So I don't know if it's always like table dash question dash answering. Sometimes they have like a weird other name for the task identifier. So it's not a perfect system in that way. Okay. So that's how to use the pipelines. And like I was just talking about, you can do the pipeline for all sorts of different tasks. So here I just have a bunch of different examples where I have called the pipeline on just a task that I want to do. So here it's sentiment analysis. Here it's named entity recognition. I think here I specified the model, but actually if you don't specify the model, this is the default one that it grabs anyway. You can ask it about question answering. You can ask it about translation tasks. And so I guess here is an example of a nuance where translation, like this is a specific language translation and that has a task identifier, but that's maybe kind of harder to know by just looking at that sidebar on Hugging Face. And you can also use it for summarization, for instance. So lots and lots of natural language processing tasks are supported here. This is not a totally complete, but you could insert a long article here, and then the summarization task is going to summarize the entirety of that article for you. So lots of different options. And then just wanted to touch on, kind of wrapping up talking about pipeline. Like I said, that we've been focusing a lot on these natural language processing tasks, but image and audio based tasks also are possible with the pipeline. Those are also built in. So if you want to just do quick inferencing on, vision based tasks, for instance, those are also easy to access. So for instance, here, I'm going to set up a pipeline for image segmentation. Here, I'm just going to download this picture of a apartment street view that I found. And so we can also, with the pipeline, just do image segmentation incredibly easily. We can see that the way that this segmentation task works is that it gives a mask for every single object that it detects. Here we have to do a little bit of finagling to plot it. But for instance, here was just an out-of-the-box image segmentation model that Hugging Face gave me because I just told it I want to do an image segmentation task. And I've fed it this image and it has, turned that image into a segmented version of here's the road and here are the people and here are the cars. And it identified that that was a roof. And so it's super easy to I just picked this, I didn't know that this was a model that was necessarily good for image segmentation. But the great thing about pipeline is that I don't need to know that. I can kind of test model first and ask questions later through this way of interacting with the models, which is very cool. Okay. Oh, thank you. Cheryl put a better link to talking about pipelines. Yeah, okay. I was gonna say, I feel like there's a list somewhere. So this is a list in the chat of all of the task identification, like those task IDs that you can just stick directly into the pipeline. And so there's a lot of options. It's very cool. Okay. So we are going to move on to talking about how we might fine tune these models, but I think we can take a short 5-6 minute break and return at, oh gosh, in Central Time, that's 10:05. So yeah, but if anyone has any pressing last minute questions before the break. Okay, then I will see you all in about 5 minutes. Okay, welcome back. I'll give people one more minute before I really get started, but I will go ahead and post in the chat the GitHub link to the next notebook we're going to work off of. Okay, so the next thing that we are going to talk about, like I said, is fine tuning the model. So let's say that you have, grabbed a model off of Hugging Face. You thought that you would be able to use it, but it's just not quite as performant as you want it to be. Or maybe you have something really specific in your data, so it's, almost as performant as you'd want it to be, but you have a data set, like maybe in that image segmentation example, you have a data set where there's like a whole ton of like traffic cones or something. And even though the model knows about traffic cones, it like really doesn't do a good job picking them out or something like that. That would be a really particular case. But, there's a wide variety of reasons why maybe a model off the shelf is not doing quite as good of a job as you'd want. And you can take that model and simply train it additionally on some more data or some more specific data to your task and get a better performing model for your task. Or you can take a model that has, for instance, a good understanding of language, but isn't trained to do a very specific thing, and fine tune it so that it is now trained to do a specific task that wasn't the original task that it was doing. So you can take advantage of the fact that it has a great understanding of language, but unfortunately doesn't do what we're going to do in this notebook, specifically sentiment analysis of tweets. But because the model already has a base great understanding of language, we can just fine tune the model to understand specifically the data set of tweets and specifically the task of figuring out the sentiment of those tweets. And it's a fairly kind of easy training step because a lot of the bulk of the work has already been done for you because the model already has that understanding of underlying language. So hopefully we'll be able to get through this notebook. I might, through times, go a little bit quickly through it, but hopefully we all get through okay. So, sorry, give me 1 second. My window is open and there's a very loud sound outside. Okay, I think that will be better, but please let me know if it is overwhelmingly loud. Okay, so like I said, in this particular notebook, what we are going to try to do is to use this tweet evaluation data set. And what this is a data set of a bunch of tweets that people have tweeted, and then a label about, what was the sentiment of that tweet. So was it, a happy tweet? Was it an angry tweet? Like, what is the basic feeling that that person had when they tweeted that thing? And in order to do this, we are going to train the BERT model. So the BERT model is an example of a model that understands language, but is not at the time trained for the specific task of classifying tweets into sentiment. But with fine tuning, we can now leverage that model and turn it into something that understands our tweet with only a minimal training. So again, we are going to do the classic imports, installs, and give it that Hugging Face token. Because also in this notebook, we are going to be taking our trained model and pushing it to our Hugging Face, which means that it will exist in a repo under your Hugging Face username, and then you can grab that model and do other things with it, which is great. Okay, so again, we follow the Hugging Face tokens page, and we put in the token. Okay, so the first thing that we are going to do is, of course, load our data set. So when we were just inferencing a model, we didn't have a data set because the data was just like, I type something in and I see what the model tells me. But when we're training, we obviously need to grab this entire data set, which is quite large. We can see that it has, oh, it's gonna download it from somewhere. But we can see that, you know, the data set just in the data set card is like a large data set that has a lot of examples. So Hugging Face has an option. It has the Hugging Face datasets package. So we've been using the Hugging Faces transformers package, but datasets is also a Hugging Face package. And they have this great built-in thing to load any dataset off of Hugging Face. So as long as the Hugging Face dataset has this .py file that specifies how to load the dataset, Hugging Face will simply grab that .py file. It'll be able to load and build the data set for you. So all that we have to do is say that this is the data set that we want to download. Emotion is just the specific version. So on Hugging Face, you're able to set up a data set to have different kind of configurations, which is going to, in this case, decide like the label. And so this is just a specific thing for this data set, but basically we just have to give it the name of the data set and it's going to get it for us. So we can see that when we've downloaded a data set off of Hugging Face, we have this structure. So it's often already divided into a train, test, and validation split for us. This helps keep the data very consistent. So it's not every time that you load this model, you have like these totally new splits, because that can lead to things getting messy. You don't know exactly what your training and your testing data is. So that's already all built in for us. And we can see that this data set features text and a label, which again, for a sentiment analysis is what we expect. The text is the tweet and the label is simply what was the sentiment of that tweet. And so here we can see one example of that. So for this particular data set, worry is a down payment on a problem you may never have. Joyce Meyer, #### is an example tweet in the data set. That is the text. And the label it was given was a 2. And we can see from the data set, okay, like a 2 is a numerical label, which makes sense. The model needs those. But we can maybe ask, like, what does a 2 mean? And we can also see in the data set that it'll tell us that in this data set, we have 4 emotions that the tweets are able to be tagged with, and that's anger, joy, optimism, and sadness. So what we're doing here is just building these 2 dictionaries. These are going to end up going into the model because they're going to tell the model how to convert from numerical labels into named labels. So this is just something that we construct so that the model can get that later, so that when we do a prediction from this model or training on this model, it is able to tell us what the numerical labels it's training on end up meaning. So here we're just constructing, we've printed out these 2 little dictionaries. So there's 4 total classes, 4 total possible labels. And we know that a 0 corresponds to anger, a 1 corresponds to joy, a 2 corresponds to optimism, and a 3 corresponds to sadness. So up here, where this was given a label of a 2, we've now learned that actually that meant that this tweet was optimistic. And maybe that's true, I don't know. I think classifying tweets into only these 4 emotions is probably a bit too narrow of a set of classes. So I think we'll see with this data set with a lot of these tweets that deciding whether or not the emotion that was assigned makes sense is maybe not the easiest thing to do. Okay. So of course, we need to tokenize. Again, we always need to tokenize. We give to a model. I'm going to, in the interest of time, perhaps gloss over these tokenizing steps a little bit because we just talked about it a lot. But basically what we are setting up here is we are grabbing the correct tokenizer for the model. We didn't talk about it in the last notebook, but Hugging Face also has these auto classes. So you can say, instead of calling a particular tokenizer, like we called GPT-2 tokenizer in the previous notebook, you can call auto tokenizer. And again, Hugging Face, because it's very smart, is going to say, okay, you're telling me you're trying to grab a tokenizer from here. Let me just go find it for you. So you're telling me you need a tokenizer. I will go grab the tokenizer, but you don't have to tell me exactly which one. I will sort through what's in that repository and I'll find the tokenizer for you. So we're using auto tokenizer here to just load whatever tokenizer this model used, and Hugging Face will do that for us because it knows. Then we're going to just define a little function to do the tokenization, because we need to tokenize the entire data set. And so we can do that with this map function and use the little thing that we defined, which just calls the tokenizer on the text, and do it for the entire data set. And in the end, what we end up with is an entire tokenized version of our data set. So now we have what we want and what we can feed into the model, which is a data set, except instead of text, we now have the numbers that the model needs. This is a little line that, again, we are going to gloss over. I believe at the bottom, there's like a homework question about it, or if you want to know more about it. But this does kind of help with how the model is going to perform during training. So we're just going to do this little step, which is going to dynamically pad our sentences, because obviously tweets are a ton of different lengths, and it's going to just pad as is necessary to make it so that feeding data in batches makes more sense. Okay, but now let's get to the good part, which is actually training a model. So here we have, again, we're going to use that auto class. So the task that we're doing is sequence classification. So we already know that we want to do a sequence classification task. So we're going to just load auto model for sequence classification. This is the model that we are going to use. And then, like I said before, where we had made those dictionaries that are going to tell us how to map between labels and actual names, we just need to feed those in here so that that model is aware of what the labels in our data sets actually mean. But it's that easy, again, to define the model, because you have this auto class and you just feed a model that already exists on Hugging Face. This is all that it takes to set up a model for us. Okay, then the other thing that we need to define is metrics. So when we were just running, a task on a model that was already trained, we didn't have to think too hard about how to evaluate the model performance, because the model performance for us was sort of a subjective thing, right? Like when I run GPT-2 on Once Upon a Time in a Land Far Away, and it gives me a story as an output, I get to kind of decide like, oh, did I like that output? Like I don't have to have a hard number on it. But during training, the model is going to have a hard number about how well it's performing. And in this case, the way that the model performs is, well, did it predict the label correctly or not, right? Our data set is already a set of tweets and a set of labels for those tweets. So how well the model performs is basically like, okay, well, was that label correct, right? I'm going to give you a tweet, you're going to give me a label. Does that match what was in the data set? And so a good metric for this particular task is just accuracy, where accuracy is just like, what fraction of the data set did you get right? But Hugging Face has a lot of built-in metrics that you could use to kind of help you better understand how the model is performing. A lot of these will kind of depend on the specific task or depend specifically on what you care about. And like I said, there's lots and lots and lots of them, and there's lots of ways to evaluate performance. So this page kind of has a whole lot on it. But for something like a classification task where there's just a correct answer and you can get a fraction of the correct answers, you can get some fraction of the sample correct, accuracy is a great choice. It's very easy for us to understand because an accuracy of 0.9 means we're getting 90% of the data set correct. And so we can very straightforwardly decide whether or not that's something that we're happy with. So here we're going to load the accuracy metric. And then this is, through the Hugging Face data sets, but there is also a way to kind of define particular metrics that you care about. And we can use sklearn to help us with this. sklearn is another sort of machine learning package in Python. I'm sure you heard of it. And it also has lots of built-in little tools for us. So one of those things is that it has its own set of metrics, and we're allowed to just define this compute metrics function, which has, where we can define kind of anything that we want to display, and we can make use here of metrics in sklearn to print out some sort of other important metrics that we might care about. So lots of options for looking at how your model's doing while it's doing its thing. Okay, now we can think about actually setting up training the model. So there's a lot of different things, again, that you can set up for training the model. This is all kind of like, Hugging Face really gives you the opportunity to have like complete control over how the training exactly happens and what exactly you're seeing about the training. So it's very cool, this list of training arguments here. So the list of things that can go into the training arguments is absolutely enormous. You can see it in this documentation here. These are all of the different things, and all 96 parameters are explained on this documentation, exactly what they're telling you. So there's parameters of, like the optimizers, those are specific to the neural network. There's parameters that are going to tell it exactly how to distribute a batch over the GPUs or CPUs or TPUs that you have access to. So there's lots and lots of potential for kind of control here. We're only setting a few things here, which is like, here's where I want you to save my model. This is saying, this is how often I want you to tell me how the model's doing. This is how often I want you to save the model to the place I told you to save it to, and stuff like that. So in general, you can totally control this to an extreme degree, but a lot of times you want to set a few of these simple parameters, which just tell you like how often I want you to log stuff and where I want you to save stuff. And the Hugging Face, again, is very smart. So it'll take care of it, has great defaults for the things that you don't set. Okay. So now we can put it all together finally into this trainer object. This trainer object is the thing that we are going to end up actually training the model with. And that'll be a very simple like trainer.train in a second. So we just want to set up the trainer basically to say, I want to train this model. So we've already defined our model. So the model that we're training is the model we defined up there. The arguments are going to be these arguments that I just defined. So that's everything I could ever want to tell Hugging Face about how to train this thing. We're going to give it the tokenizer. We're going to give it that data collator that we talked about for like a millisecond, which is just how to kind of stitch together all this data and make batches. We're going to tell it what data to train on. We're going to tell it what data to evaluate on. And we're going to tell it what metrics we want to see while it's training. So you just set all of those things directly into here. And then we can actually train it. There is another tiny aside before we actually do the training, although I'll get to the spoiler, which is the training part is just doing trainer.train. So once we've set up that trainer, we basically just say like, okay, now do it. But here we're just doing this small thing of, it's possible to change this model init, to just change exactly, to tweak exactly what model we're using here at the start. And so you can grab a specific model through defining this little model init function. You can grab like a specific checkpoint of a model or a specific version of a model, and kind of dynamically just change exactly the starting point. Because when it grabs the model, it is grabbing some version of the model which has already been trained in some capacity. And so you can just kind of specify here like some other exact particular instance of the model. And we've made a note here about how generally you don't do this unless you're just experimenting around. A lot of times you will just grab the model and just train the model. But this is a thing that is kind of possible to do, to make this little tweak and kind of experiment with potentially a different checkpoint or potentially a different version, still kind of at this point right before you train. Okay, if you've been running all your cells, I have not been running all my cells. I've just been going through this. This will do the training set. I'm going to run all these, but I don't know how long it'll take. It will do the training for you. And this training takes not a super long time because this isn't a gigantic model, but it's also not short. It takes a couple of minutes. It takes like a little bit longer than you want it to take for teaching a class about it. But, oh no, oh no, oh no. Things aren't defined all the way up. Did I not run something like forever ago? Okay, wait, I'm just gonna set this going and then we'll see. We'll see what happens. Oh, I shouldn't have run the cell because now it goes over the, that's not the right repo. Sorry, while we wait, while I let that do its thing, I do want to just talk about the things that it prints out while it's training, because the training will take a second, but it is going to print out a few of those things that we asked it for while it was training, right? So we can see here that we are getting the training loss, we're getting the validation loss. We gave it both a training data set and a validation data set, so we can compare how it's doing on both of these. We're getting those metrics that we specified. So we made this compute metrics function, which contains in it, where did it go? We made the compute metric function from the sklearn stuff here. And we specified that we want the precision, the recall, and the F-score. So we can print that out. We could have specified that we wanted, the accuracy, like I was talking about, into that compute metrics function. But we can see that while training, we're getting all of these things that we told it that we want to see printed out while training. And we also set up here that we want to train it for 3 epochs. So we can see that it did train for 3. And then we also see up here that we set it to the evaluation strategy to be every epoch. So again, we're at the end of every epoch, we're seeing these this information that we asked for. I think also, again, in the homework down below, there's kind of the option to discover what training in steps looks like. And then you'll see more frequent evaluations of model performance, which can be really, really good when your data set is super gigantic. So 1 epoch means 1 pass through all of the total data. But if your data set, let's say, is like 10 million things, right? Like 1 epoch might take, like 3 hours. And maybe you want to just have some semblance of how it's doing before then. You can set up this evaluation strategy to be instead in a number of steps. And so every time it passes through some set number of batches of your data, it'll give you these metrics then, and it gives you some idea of how the model is training without having to wait for like this entire step to complete, because that sometimes just takes forever. Okay, so this line here, well, this notebook is giving me problems. So, but this line here is going to be how we would push to hub. So after you've trained a model and you're happy with it, you can again just take that trainer object and do a trainer.push to hub and push this model that has been now trained to your Hugging Face hub. And so for me, I have now on my space, you can see that there's a models section on my Hugging Face page. So this is the BERT emotion model that we just trained, and it has pushed everything that it needs to, understand the model that we just trained to Hugging Face for me. So that's all there, and it exists now for me just in that one push to hub line. I would have to go and enter some of these things about the model card. It's not going to do everything for me, but it fills in a lot of stuff really easily, and it creates this hosted inference for me. So a lot of kind of the work is taken out by simply just sticking the model on Hugging Face, and then Hugging Face takes care of a lot of that for you, which is very cool. Then there's a few things. Oh yeah, sorry, do you have a question?
Yeah, I guess something I've heard, I think in the past, is once a model is trained, like GPT 3.5, you can't really fix it, it's done. So all you can do is use it. So what are we, but it seems like we are fine tuning an existing model. So I'm just trying to understand what is possible with a model that's already baked versus what is not.
Yeah, so I mean, it is theoretically possible, and we'll talk about it a little bit later this week, to fine tune or train additionally a model like GPT-3. Even, I mean, probably not for like you or me, because I think you need a better computer, but it's theoretically possible to additionally train a model. Now, the thing about something like GPT 3.5 is that it's been through these additional steps of instruction fine-tuning and reinforcement learning from human feedback, which has kind of fundamentally changed the model. So you'd have to go back to that base version of the model and do some additional training, and then kind of redo those steps if you want to get all the chat functionality back. So that's a bit of like a challenge. But for a lot of these models, like the BERT model, it's quite small, and it already has been trained on a lot of data to have a pretty good understanding of just like human language. But it might not like do a particular task that you want it to do, right? So even though it was trained to have a pretty good understanding of human language, it's not trained to like very specifically decide the emotion behind a tweet, right? And so that's kind of an easy task to say like, okay, well, if I have this great data set of tweets that I want to classify, like I can take advantage of all of the learning that the model already has and do this extra little tweaking step and probably get it to get better performance on my specific data set, but without like this heavy load of like training a model entirely from scratch and like that type of thing. Does that make sense, or does that not answer your question?
Yeah, I guess I'm just wondering, like, so what everything you're doing here, is it basically similar to me telling ChatGPT, hey, here are 3 examples, and now create one more example just like this? Or are we just, is that something different from what you're doing now? Is it, or is it basically the same?
Yeah, so I mean, what you would do with ChatGPT would be different. So you could take advantage of ChatGPT's ability to understand and ask it the same sort of thing. But what we're doing here with fine tuning is we are literally changing the weights of the model to suit the specific problem that you have. So when you do a fine tuning step here, we're actually adjusting the model to better fit the data. So you're not taking advantage of that the model understands language and that like you can speak to it and ask it to do a task like maybe you would on like a ChatGPT thing, but you're tweaking the model to do a specific thing that you want it to do better, or to introduce it to more data that you think that it didn't have as well. And then after that, it's kind of like the model should be universally better able to do the task that you've fine-tuned it on, because you've literally edited the model in place to better suit your task. The other thing is that while you could maybe give ChatGPT, in the chat function, like an example of 10 tweets and tell it the emotion of the tweet, or probably it's okay at understanding the emotion of a tweet, something simple like that. It's oftentimes hard to run that on like huge data sets. You know what I mean? If you had like 10 million tweets that you wanted to classify, that could be a challenge. But here you kind of, once you have the model that classifies tweets, like then you just run it on those 10 million examples, and you don't have to worry about doing that lift of like giving examples and getting feedback every time and that sort of thing,
Yeah, thanks.
Are there any additional questions? Sorry, I see things popping up in the chat. And I very much appreciate you guys answering those because I'm not good at reading and talking at the same time.
Yeah, actually, one more question. I do notice that with OpenAI, they do have models available that OpenAI says we can fine tune and customize. I think they have the Ada, Babbage, Curie, and Da Vinci models. Curious if anyone here has any more information on those, whether they map to GPT-3, 3.5, 2, 4, something, or how to think about that.
We've had projects where we've done additional training on those models through OpenAI. The Da Vinci models and the other models that are GPT 3.5, keep in mind that those are not the chatbot. They haven't undergone the reinforcement learning from human feedback. They're more of the sort of raw model like you're looking at with the GPT-2, but a much larger, more advanced version. And you ship your data up, and then they actually do the training or supervised fine tuning of the data up there. They're too large to train locally. But keep in mind, those are not the chatbots. The chatbot undergoes additional training called reinforcement learning from human feedback, usually. And that's what turns it into sort of a collaborative, helpful, response. That's where the responses come from. Once you do reinforcement learning from human feedback, it's not really possible to do additional training on that model anymore, because that changes many of the parameter weights in a way that disturbs further development of the model. It sort of locks it into place because it's responding in a particular way now. So it's not good for additional training. So when you do training up like Da Vinci or other models of different sizes up on OpenAI, what's happening is you're getting another thing like GPT-2, but it's a much more advanced one where it's just a large language model that you can use to do tasks, but it's not going to be a chatbot. Hope that helps.
Yeah, and I guess on the reinforcement learning part, I also hear OpenAI saying ChatGPT learns from your chats or whatever. What is, like, how do I reconcile that with the fact that once reinforcement learning is done, it's done and the model can't learn?
Yeah. So they will do additional, keep in mind that when they say they're learning from your chats, remember we're giving the up or the down, right? You're voting up or down. So very likely what they're doing is they're doing additional reinforcement learning. You can do additional reinforcement learning, but you can't do additional supervised fine tuning where you're changing the knowledge of the model, right? So you can further modify the behavior of the model, but it's not going to learn anything more. But you can continue to do reinforcement learning on it, but it's not, you're not training it on a new domain, you're not training it on new information or new documents. Instead, you're modifying the behavior further based on the feedback that is gotten on what are the preferred responses. Like, so if you say thumbs down, you didn't really answer my question. Well, then now it knows that the later response it gave was preferred over the earlier response that it gave. And so now you can do some training on that.
But doesn't that change the weights of the model?
But it's changing in two different ways. When you're training using supervised fine tuning, where you're having the model learn new concepts, train on new documents, things like that, that's called backpropagation. And backpropagation is tied directly to the model itself. So, and you can do that, as much as you want to, right? You may, you can keep on doing that. Once you start with reinforcement learning from human feedback, you really are changing parameters very broadly across the model, and you're doing so against an external objective function. That's not part of the function, right? So it's external. A human would prefer this over this, or something that's responding to a human would prefer this over this. So, and once you start doing that, you can keep on doing reinforcement learning from human feedback. But right now, so far as I know, you can't do the gradient descent anymore. It disturbs properties of the network that are respected by gradient descent. They're not respected by reinforcement learning from human feedback.
Thank you.
So assuming we have train the model, which in this notebook, the outputs have a trained model. And then optionally, we've pushed a hub. There is a note here that depending on the size of your model, this step could take forever if you decide to run this notebook on your own. The BERT model in particular is not super huge, so this doesn't take too long like as is, but you could edit this notebook to, find a compatible model / data set on Hugging Face and experiment with that and make kind of fairly simple edits to this notebook to kind of play around with that and see what happens. But depending on the model you choose, that could be very large, and this sometimes takes a super long time. So just to know. But given that we have our model, we've now trained it, we did trainer.train, there's other functions we can do, methods of trainer that we can look at that'll kind of tell us more about the performance. So the first thing that we can do is do this trainer.evaluate and basically ask how well did the model do. And so we are in this case evaluating on the trained data set. So we're asking it how well does the model do, but on the data that it was literally trained on. We could instead do stick in here the validation, because that was our validation set, or stick in test, and it would give us these same metrics, but on that different data set. But here we're asking it, how are you performing, but on the data that you've seen before. And this is going to print out for us a lot of things, this set of things, which is kind of going to tell us, for instance, the loss that it got to. It'll tell us what how many epochs it was trained for. It'll tell us how long it took to perform the evaluations that we've asked it for. It'll give us those metrics that we were printing out. So the precision, the recall, the F-score. So this is a great way to sort of, if you've already trained the model, yes, you print out some of this information up here, but you can also get this kind of overview of performance just through this trainer.evaluate. And you can also get this overview of performance. Like I said, instead of just on the trained data set, you can do this on like the validation data set if you want to know the performance there. So it's very useful to kind of see how it's doing. But a lot of times, in order to see how a model is doing, really what you want to know is like, what are you giving me for the particular data? So then probably what will come more in handy is doing something like a predict. So here we can again take that same trainer object, but we can do a trainer.predict and ask it to predict the answers for, again, here we're gonna do the training data set. So here we're asking for an output for each, sorry. Here we're asking for an output for every single object in our training data set. And so here we could then actually like inspect what label it's going to assign for every single thing in our training data set. And so we can look at actual examples of what is the input that I gave you and what is the true label that I wanted you to predict, and then what is the label that you ended up predicting. So we're going to take this preds object, which kind of contains a lot, and turn it into something that's a little bit easier to look at, namely a data frame. And then we can also do a confusion matrix. So again, here, scikit-learn is a great tool for when you want kind of these little extra metrics for any kind of machine learning stuff. So here from sklearn.metrics, we're going to import the confusion matrix. They have a great thing for just building a confusion matrix from a set of true and predicted labels. And if you need a refresher on confusion matrices, they're this thing that looks like this, where basically for every class, it tells you what number of things was classified as that thing. So for something that is truly anger, 1,376 items in our data set were classified as anger. But for instance, something that was truly anger, 8 items in our data set were miscorrectly identified as joy. So generally, a really good confusion matrix that you want to see looks just like this one, where it's kind of hot along the middle. That means everything kind of corresponds, like the diagonals all mean that the predicted and the true tend to be the same thing. And you want to see not too many values around here, which is telling us what is mispredicted, because these things are not a match. But it does help you understand, for instance, if this pixel were like even hotter, this was like this color, right? we can better understand that, sadness and anger are maybe like emotions that are getting really confused in our data set, and that can help guide us to add additional data, reevaluate how those things are labeled, all of that good stuff. So here we're just going to turn that set of predictions into a data frame so that we can better look at it. And then here we're also going to make a data frame of just the misclassified predictions, because sometimes, those are the most interesting. If the model gets it right, you're like, oh, well, then it was an easy problem. But when the model gets it wrong, those are the times that you want to, ask yourself a little bit more. And I'm sorry for the tweets are not always friendly. So I've tried to make them for the most part friendly, but don't read them too hard. But for instance, here we can look at like the data frame of just our misclassified, and you can see, for instance, this tweet was predicted to be anger, but the true label was sadness. So we've marked that through the code up there as being a misclassified example of our data. And again, we just talked about the confusion matrix, but we've also plotted this confusion matrix so we can better understand whether or not sort of particular emotions tend to be getting mixed up. It looks like, kind of from just a cursory look here and also from this confusion matrix, like I wouldn't firmly say that two of these emotions tend to be confused too much, which is maybe good news. Versus you could kind of expect maybe joy and optimism are very related emotions and it would mix those up or something. But at least in this data set, it doesn't seem to. And then we can, of course, look at specifically some examples. So here we're just going to query that data frame that we've created, and we can, if for instance, joy and sadness seems to have more examples than we would expect, we can query the data frame and look at those particular examples here. So here I've asked it for things that have true labels of joy and predicted labels of sadness, just print me what those things were. And if you maybe read through some of these things, you can maybe see why that would be true. I mean, and have social anxiety. There's many awkward things wrong with me. The true label for that was joy, because I guess this emoji is trying to be funny. But you can maybe understand why the model thought that was, an upsetting sentiment rather than something happy. So we can kind of also just inspect these examples and see if they make sense to us and kind of see what maybe went wrong. And if we'd want to change some of our labels because we don't agree with how the data set was made. Okay, so the other thing is that now that our model is on Hugging Face, we can use it just like we used the model in the last notebook. So we've done all of the training step and we've done the push to hub. And this model now exists in two places. The first place that it exists, because I pushed to hub, is in this is my username /Bert emotion, because I pushed it here. So it now exists as a model on Hugging Face that you could look up and use like any other model on Hugging Face. But it also exists right now because I saved it locally. Oh, well, okay, right. I didn't rerun this, but it would exist right now because I saved it locally in a folder that's called Bert emotion, because up here, we set in those training arguments to save it to an output directory called Bert emotion. On Colab, keep in mind that if you do kind of do this training on Colab, if you don't do this push to hub and you only save it locally, if you don't download that model at the end of your session, Colab will delete it. But if you were doing this on your own computer or on a computer where things do not get deleted because it's not Colab, then that directory would contain everything you need for your model and it would just be saved locally to your computer. On Colab, we can act like those things are local, though, at least while we have a session. So we could, for instance, now run this model through the pipeline, and we can do this locally. So we can create a text classification pipeline and grab our model from the Bert emotion /checkpoint directory. But because we pushed it to hub, we can also just use that model through this line of code exactly like it was any other model that existed on Hugging Face. So in this case, I would just specify model equals a petulante / BERT emotion, and Hugging Face would go and grab that because it now exists online as the model. And I can run it like I run any other pipeline model. So I just call emotion classifier, the name of the pipeline, on data, and it will do it for me and give me the label and the score for just an input line of code. So now that I've trained the model and I've done that work and I've pushed it to Hub, it now operates as simply as any other model, and you can do this inferencing step on it extremely easily. Okay, so at the bottom here, there's a couple of like optional homework, more just kind of like things to think about, stuff that maybe wasn't covered super in detail, where you can kind of ponder additional kind of questions, additional things that you could do in this scheme. So that's kind of like left up for, on your own time, or if you want to look at that during office hours, and we can answer questions about it during office hours. But yeah, that is kind of how to basically fine tune a model. I see a lot of activity in the chat, so please let me know in this last 10 minutes if you have questions. Yeah, Michael?
I guess, can you, I'm not sure if this is the right question to ask here, is basically how the model typically is saved. I know sometimes you can save it as a deserialized object or some kind of, particularly for this kind of models, how it is actually saved, persistent, right?
Yeah, so I believe that it's normally some set of this config, which helps specify like what the base architecture will look like, and then a bin file, which I believe contains the actual like weights for the model. And I think that they're usually saved like that. I have seen, I don't know if in the push to Hub, what level of specificity on exactly how to save you have control over. We should check out the documentation. I think probably a lot, because some models are saved in like, split up into like 40 of these .bin files. And so like, it's, tons and tons of weights files and stuff like that. So I do think you have some control over how exactly it's saved here, but that is the kind of general construction, is a .json, which just like specifies the metadata, and then a .bin, which gives the literal values for the checkpoint.
Abby, would you want to take a 5-minute break before we go into office hours then?
Yeah.
Cool.
And thank you so much for coming, everybody.
Great. Thank you, Abby.
I had a question. I was looking at the documentation for the Hugging Face when I was trying to do the homework stuff, like the map method. What does unescape mean on the, like, what does that term mean when you say unescape, the HTML stuff?
Sorry, I'm muted. Wait, where exactly? Sorry.
So on the homework, it says like expanding our knowledge of data sets, map method. There's like a link to the Hugging Face course. I click on it. What does the unescape HTML mean on that Hugging Face website?
Oh, that, okay, so I don't know exactly, and I think Sharo might be able to answer this better, although also, but I think that is just a thing about the way that like web code is generated, where like there's a bunch of extra like HTML stuff when you get like when you like web scrape stuff from websites, and I think that the unescaped is just trying to is like this.
Eliminate that.
So I think she might have frozen up a little bit,
Yeah.
unfortunately. So actually in that link to that Hugging Face course, if you, so it will be most helpful if you
Things from that comes from an HTML source, exactly the details.
Yes. So yeah, exactly. So I would suggest scrolling all the way up and just kind of reading through map. But in the course, it talks about, so I don't know if you've ever like copied something from HTML, but it usually has like these little annoying like set of symbols that are meant to take the place of another symbol in HTML. And it's basically making those, it's basically resolving those character codes into something that's like a readable, something helpful.
Oh, sounds good. Thank you.
Okay.
Hi,
So yeah,
I
I
have a
think,
question.
yeah.
I don't know actually know if this is a question or a thought or how to just going through the content over the last 2 hours. It, it seems to be that, you know, kind of recency bias or, you know, with the amount of content that's getting created or added to kind of contemporary kind of thought, how or what is the challenge, or I see the challenge of updating or training models to recognize things like, you know, sarcasm. If you're looking at classifying, you know, context or putting things into context, you know, the different ways in which, you know, sarcasm versus, you know, real kind of thought. Um, Again, I don't know if this is a thought or a question or what, but how are data scientists or how are people in the AI field thinking about um, categorizing that or identifying it or using the models to actually categorize it?
Yeah, I don't know about work right now, maybe somebody else does, about kind of like specifically handling that. I think of a lot of times the attitude right now is that a large language model that has been trained on enough of kind of human language picks up on some of those sort of subtleties. So you know, through reading lots of tweets and, you know, text chains and like human interactions, it sort of starts to learn when sarcasm is appropriate and when something is likely to be sort of literal versus metaphorical. And I think right now that's kind of the primary sort of way to approach language, is that if a model sees enough of human language, it will have sort of the same understanding that we do of human language, where maybe sometimes you're confused what somebody means, but a lot of times you sort of just by the context of the conversation and the tone and all of that stuff, you're able to pick up kind of what somebody must mean, even when you're not able to like figure it out in isolation, you know, if that answers your thought question, I don't know.
Yeah, sort of. I mean, it's difficult enough for humans to understand when somebody, you know, a person is being, you know, sarcastic or actually real. And if we're just using the words in and of themselves, or the you know number of times that those words are being used, it just kind of it's a thought that I had or tried to understand, you know, on my own.
You can imagine that that sometimes information is not carried in the words at all, but for very short context, interactions, you know, like if I say really, really, you know, very different meanings. But if you have enough context, then it might be able to disambiguate what you mean. But if it's short, then it's going to be pretty tough. But remember, a lot of information. It's a lot of the information that we get is not, if not completely duplicating, is related. If you're speaking sarcastically, for example, there's probably going to be clues in the larger context that the proper response is a sarcastic one, or that you yourself usually, you know, invoke that, and your style of speaking over the long conversation may, you know, so sometimes it's not the only source of information, but we definitely, you know, if you're doing text only, then and it's brief, then it's a guess.
Oh, and it could also go back to the point of the ways in which the phrasing or phrases are tokenized, right? Because again, if it's just characters, words, or you know, you have larger chunks of the subject pool, then the context may actually be derived from how large those tokens may be. Is that possibly?
I would say you almost need to divorce tokenization from the meaning that gets derived later. It can make it harder to get meaning from it, but it doesn't, so long as the tokenization covers the language, right? If there are parts that it's not coding at all, then it's not going to be able to learn that. But otherwise, it's going to be able to learn it. So no matter what's happening with that tokenization, even though it may be a crummy tokenization, it's harder for the model to learn, but you train it enough on enough data, it's going to be able to learn it.
Are there
Yeah.
any just general rules of thumb for, I'm trying to help a friend. He just has an iPhone. He doesn't have any type of PC. And he's trying to get Bing to work closer to how well it can work on a laptop. Are there just any kind of generic?
Now, I don't know about Bing, but I know that OpenAI just released maybe iOS based or certainly phone based interaction. Okay. So there's that, and there's also POE.com, which started as a phone only app. Abby, can you think of others? Those are the two main ones.
Okay.
Yeah, I was going to say Poe because I think that's kind of the big Apple based one right now.
And just as an amusing note, I think it would be interesting to see how many answers it comes up with for context for the Southern phrase, bless your heart.
And it's going to vary. I think it's going to vary by the size of the model and what it's been trained on. That's great.
It's like, bless your heart and aren't you sweet, kind of rank up there for me personally. With nothing's wrong, I'm fine. Those are ones I thought would be interesting examples. All right, well, thank you for your time. You have a good day.
Joshua?
Yeah, thanks. So I asked a variation of this question the first week, but now I think I have a much better understanding of the tools at our disposal based on this class. But if I go to ChatGPT right now and I say, write the beginning of the next chapter of War and Peace, it'll do it, and it'll know the minor characters, and it sort of has a full understanding of that. So now I have, let's say, my own book that I've written 2/3 of it, and it's 500 pages. Let's say I'm heading toward War and Peace, and I want to do the same for my own book. And one of the ways I could do it is to use LangChain and try to kind of it'll pull some sections out of my book and supply it as context. But I think could I use something like fine tuning for that? I wanted to basically treat it as if it's been trained on my data set as well. And how would I do that?
I think that's a great question. Should mind if I start answering, Abby?
Sure.
So yeah, I think that's a really good, insightful question, because you're right with LangChain, it'll be able to pull up sections, but only what fits in its context, right? It'll pull up sections, but it's not getting at overarching themes or new types of concepts that you've introduced. Or let's say that you're writing science fiction, and so it doesn't know about this society in the future that you're writing about that has these complex ways of interacting. And for that, you're right, you would need to train the model. So, and there's always a trade-off of a model that you might be able to train might be smaller, or if you want to do more extensive training. So do you do something like a Llama 7 billion parameter or something, but it's going to be less of a fluid writer, or, you may ship it all up to OpenAI to train like a Da Vinci. So you can train models that are like GPT 3.5, that sort of level. And there are smaller models that get about that performance as well. But again, it's not going to be a chatbot, right? It's going to be, so you're going to have to do more extensive kinds of prompting to get it to do the things that you want it to do. But it can certainly be done. But those types of things that'll learn through the training, it won't be able to do that using the LangChain. So training is when it needs to learn whole new concepts or a large body. And again, it's not memorizing, right? But it's learning themes and, ideas. So you're right. That would be, that probably should be fine-tuned, should be additionally trained.
Okay. Thanks. That's that's interesting. And the model that we looked at the notebook today was the fine tuning was here's the input and here's the expected output. So how do you, can you fine tune with just kind of raw text, like understand this text, and what is that process called?
So that's just another kind of fine tuning. I call it domain adaptation, but that confuses people when I do it. But that's what it does. Supervised fine tuning of a masked of a word masking task. So, you know, just like the models, many of the models were originally trained, mask this word or mask a certain percentage of the words, fill in the missing words, and then you do training on whether it gets it right or not. And if it doesn't get it right,
Okay.
you train it some more.
Okay, cool. All right, that's great. That gave me some good places to look.
Yeah, I
Thank
was
you.
going to just say that, yeah, BERT, the model that we trained to do emotions, was originally trained as a masking. So like here you can see that, you know, you can take text and just take out a word and ask it to fill in whatever
Okay.
must go there.
Got it.
And that's a really
And
common
for the
way.
fine, oh, sorry, I didn't mean to interrupt you.
I was just saying that's a really common way to like train on, you know, I have just a set of text and I wanted to just understand the text. Then this is kind of, so BERT was trained on tons and tons of text to do this exact task originally.
Got it. And do I have to write the code that masks out random words? And okay, that's all somehow built into the code to make it easy.
Yeah, depending on what model you're trying to train, right? Like BERT is not really for text generation. It can do it, but it's not great at it. So you'd want to have something like a GPT style, you know, so something like, and you might, if you're really writing, you know, you want something that's well written, then you're going to want to have a larger model. So that's going to be something like one of the much newer models like Alpaca or Red Pajamas or something like that. Those are actually instruction fine-tuned as well, or like Bloom, you know, which can be a very large model. So and they'll have different methods for doing this type of training. Yeah, you don't have to code it up all yourself.
Okay. And from my understanding, the fine tuning, it's just kind of like the very last layer of the neural net.
No, it can be all the way back. As a matter of fact, if you're
Okay,
doing something like
okay.
that, it's probably going to be all the way back. There are very sophisticated methods that train only specific parts of it, but usually, so when you have a task, yeah, sometimes you can train just the head, and so you're just getting the head, but the performance you can get out of that is going to be, you know, if you really want to improve, then you let the training, that back propagation, go all the way back into the model. And then you can get significant improvement. We have a link to a book in the emails that we sent, which is Natural Language Processing with Transformers, which goes into depth about that. And there are much more modern, the book came out a year and a half ago. There are much more modern approaches that that do it in a distributed and very sophisticated manner, so you can do a lot of training of even the largest models on modest hardware.
Got it. Okay, thanks so much. This is super useful. I appreciate it.
I just wanted to say thanks for that conversation. That was my question, and you just answered it. Also along the lines of what you had said during class, trying to figure out how the additional training can happen without altering the sort of the guts of the model farther back in it. But it sounds like it actually can, and the sort of thing we were doing today was more like training ahead. Does that sound right? Okay.
And keep in mind, if you're doing back propagation, you know, then it's fine, you know, go all the way back. If you're doing supervised fine tuning, if you're doing things that are back propagation based, then what you're doing is you're moving the model in a reasoned way towards a goal, towards a solution. Bad things can still happen. You can unlearn things that you knew before, or it can, right, you can disturb that, but it's nothing like reinforcement learning from human feedback. Human reinforcement from human feedback is like rewiring the brain, in very particular ways, right? And it's going to work, but you're really disturbing, you're muddying the waters. Like if you do back propagation, the normal type of training that we do, back propagation, then the model can remain well calibrated, meaning it has probabilities that are associated with the responses that it gives you. So how likely was this phrase to be generated? You can calculate those. Once you do reinforcement learning from human feedback, where you're trying to do a wholesale reshaping of the responses, so it doesn't do unsafe responses or rude responses or acts like a chatbot, you're changing so much of it that it loses calibration. So it works better and responds how we might like better and more helpful, less harmful. But then it's kind of locked in. You can do additional reinforcement learning, but you're not going to be able to go back and then start doing some back propagation on it so it can learn new concepts.
Got it. Okay. Thanks so much. Really helpful. And thank you, Abby, for the class today.
You're welcome.
And then Ann?
Hi, so I have a question that's kind of related to what we were covering more last week, but I was going through a little bit more of the LangChain docs, and from what I understand, at a high level, from a high level conceptual standpoint, an agent uses chains which use tools to create a custom chatbot. And I was just wondering if I have an API that I want to call in real time because I need access to sort of constantly updating data, then would I want to create a sequential chain, or would I want to create an agent that uses at least if I go on the docs under agents, then tools, there's call the API. Would I be wanting to use that, or would I want to use sequential chain instead?
So I think it kind of depends on what you want to do. If you're doing something that uses agents already, then yeah, on the docs where it tells you how to access pretty much any API or just create your own tool. You can use sequential chain, but you would need some way to access that API. So you would need to already encode accessing the API. So I'm just kind of uncertain of what exactly it is you're wanting to do.
So earlier I was scraping this website Transfer Market for injury data of soccer players, but then I found a script, or not really a script, it's an API that a third-party API that someone else created that is accessing in real time the database, so I don't have to constantly scrape every so often. And I just want to figure out a way to integrate that third-party API with OpenAI's API so that I can create a customized chatbot that has this injury information in real time.
So I guess there's a couple different ways. You could either just have your script get the data from, because it sounds like you want it to answer questions over this database. Is that correct?
Correct. Yeah, I want to sort of narrow the scope of what it's looking at to just what's in the database.
Okay, yeah. So then you would want to use something like a vector store along with the question answering over a database chain. As far as getting the information, fetching the information, I don't think that's really a LangChain thing that you need to do. And if someone else knows of a better way to do this, but it kind of seems like you want to fetch the data from the API and then put that into your vector store. And that's kind of a separate thing where you're setting up the data in the vector store, and it's not really involved in sending that to a model quite yet.
Okay, so I guess first steps would be figuring out a way to populate this vector store.
Yes, you need to put your data in the vector store, exactly. And so, you know, if you need to do regular updates on that, you can. Yeah, I hope that makes sense. I think when you're talking about agents, it kind of confused me. But agents are more for when you need your model to make decisions on like what source it should access. So if you have two databases and you're like asking it questions and it needs one database for certain kind of questions and another database for another kind of questions, that's where the agent comes in, where it's making a decision. But as far as accessing the API and updating the data, that's not really what an agent would do.
Got it. I guess then for future steps, once I do get this working, if I had injury data from, let's say, basketball, right? Is that when the agent I would have to create my own agent, because now we have to decide between one of two sports?
If your question depends on accessing the specific databases, and if you want it to be able to make that decision by itself, yes. You don't have to do it that way though. If you just want to say, use this database to access to answer this question about basketball, now use this database to answer this question about another sport. It's kind of just if you want that decision making to be automated. In that case, you can use an agent.
Okay, I think that makes a lot more sense. The first step would be to, I guess, first populate the vector store,
Right.
then have my own chain, and then if I ever do want to get into accessing multiple databases, then I would need to create my own agent.
Yeah, if you want it to switch between databases without you telling it to. Yeah, exactly.
Okay, and that sort of decision making could be done by the OpenAI
Yeah.
API.
Yes,
Okay,
you can.
thank
Yeah,
you.
because you just give the agent whatever model you're using. So if your model's the OpenAI, then you just pass that into your agent.
Got it. Thank you so much.
No problem.
Any other questions? I think we'll, Abby, if it's all right with you, we'll close up office hours if there are no other questions. All
Yeah,
right, so
thanks.
see you all tomorrow.